AP Chemistry, we're in Unit 13. It's a unit called Electrochemistry, and in a nutshell, this unit deals with how batteries work. So the activity series, we've done this already back in lesson 35, but we're going to review activity series. So the activity series identifies which elements will react with an ionic compound to create a single replacement reaction. So we'll see an example of that in a moment. So if the lone element is above the cation in the ionic compound, then the lone element passes electrons to the cation and the reaction will take place. If the lone element is below the cation in the ionic compound, then the reaction will not take place. So you'll see an example of that here in just a minute. So this is a single replacement reaction. So right there, we're gonna show you two ionic compounds first of all. So zinc and chlorine will form a compound called zinc chloride, and what you see is that zinc has a 2+ charge and that chlorine has a 1- charge, so that means you're going to cross the arrows and need two chlorides to match up with one zinc. So two of the -1s for chloride matches up with one of the 2+ for zinc, and that forms an ionic bond. Calcium would similarly form an ionic bond. Calcium takes on a 2+ charge, chloride a 1- charge. So again, you would need two chlorides to match up with one calcium. So that's just basic ionic bonds going back to the foundations unit. So now let's take the single replacement reaction. Calcium plus zinc chloride will produce zinc, a metal zinc, just an atom, not ionized in any way, just a normal zinc atom, and calcium chloride. So the question is, will that reaction take place? Or will the reverse reaction take place? If you have calcium chloride and zinc over on the right, will they switch places to form calcium and zinc chloride? So we're going to see if this reaction in this direction will work. So calcium has a 0 charge. Zinc has a 2+ charge. Again, you get that straight off of your charge number by ions sheet. And then the chlorides have a 1- charge. You can either get that off the 60 common ions, the charge number by ion sheet, or just looking at a periodic table. If you remember how to do it, how to know that chloride has a 1- charge. It wants to pick up one electron to be like the nearest noble gas, so it's going to take on a 1- charge. So you're going to need two of those to match up with the one zinc, which has a 2+ charge. So 2+, 2-. Zinc over on that side is then going to be a 0 charge, and calcium chloride is going to be the same, 2+ for calcium and a 2- for the chloride ions. On the reactant side, that's the left, the calcium atom is electrically neutral. It's just a normal calcium atom. The zinc is a 2+ cation in the ionic compound zinc chloride. Okay, so here we create the ionic bond. So the zinc is going to pass 2 electrons to chloride, the chlorine atoms at this point. They have high electronegativity, much higher than zinc, so they're going to pull electrons away from zinc. This is a normal ionic bond. And so again, you need 2 chlorides because each one can only take 1 electron in. The zinc gives off the 2 electrons. So now you have zinc is now a 2+, and the chlorides are now a 1-. So then over on the right side, you have zinc, which is a 2+. That's represented by the 2 circles, which mean that it's missing 2 of its electrons that it would normally have in its ground state or natural state. And then the chlorides are 2-. So the charge numbered by ion sheet indicates that zinc has a 2+ charge and ionically bonds with 2 chloride ions. So there it is again. So the question is, will those electrons, if you have zinc chloride and calcium, will those 2 electrons in calcium be passed over to zinc? Is zinc strong enough? We know it's not strong enough to take them back from chloride. They were just taken away by chloride. Chloride is stronger. But is zinc strong enough to take those 2 electrons away from calcium? So that's the question. So a single replacement reaction will take place if zinc can take 2 electrons from calcium. And will this happen? So there's the question mark. So the electrons fall down the activity series. We see the activity series there. And electrons fall down the activity series. That's the expression we use. So zinc lies below calcium on the activity series. This means that calcium will pass electrons to zinc. So a single replacement reaction will take place if the lone element is above the cation. So the lone element being calcium is above zinc. And it is. So the electrons will get passed from the calcium over to the zinc. So we'll see that happen right here. So there go the electrons over to the zinc. Now, the zinc is no longer a 2+. It's now electrically neutral. It's now a 0. So it doesn't have any reason to want to continue to be bonded with the chloride, a 2-. By contrast, the calcium has now turned into a 2+. So it does want to go over and bond with the chloride, a 2-. So they're going to switch places. So there they go. And now you see the zinc is now a 0. It's back in its natural state again. We're assuming all the other zinc ions, electrons are there. And the calcium is deficient by 2 electrons, and so it's a 2+. And so it's going to bond with the calcium chloride. That means the zinc and the calcium did switch places. So again, just follow the rule that if the lone element is above the element that's the cation in the compound, then the lone element will give its electrons up to the element to the cation in the compound. So calcium will give up its electrons to zinc. Okay, so same reaction. We're just looking at it a second time here. On the reactant side, the left, the calcium atom is electrically neutral. The zinc is a 2+ cation in the ionic compound zinc chloride. The chloride is a 1-, but you have 2 of them, so it's 2+, 2- to form the ionic bond. On the product side, the right, the calcium passes 2 electrons to zinc. This gives zinc a 0 charge and the calcium a 2+ charge. This causes calcium to trade places with zinc, and calcium forms an ionic bond with the chloride ions. So again, electrons fall down the activity series. If the neutral element is above the cation on the reactant side, the reaction will take place. So use the activity series to determine if each single replacement reaction will take place. And I'm not going to give you all the examples that we did back in lesson 35. So here's the same one. And we said that that is going to take place. Yes, the calcium is above zinc on the activity series. Now we take the reverse reaction. Will zinc switch places with calcium in calcium chloride to form calcium plus zinc chloride? So we go back to the activity series. That would require zinc to pass electrons up to calcium. You can kind of use the metaphor of gravity. Electrons can't flow uphill. It's not really literally uphill, but they can't flow from something lower on the activity series up to something higher on the activity series. So no, that reaction will not take place. So no, zinc is below calcium on the activity series, so reaction number 2 will not take place. Now this is an overview of electrochemistry. Electrochemistry deals with the use of chemical reactions to create electricity. Essentially, how do batteries work? The study of electrochemistry centers around a class of reactions called oxidation reduction reactions, also known as redox reactions. Redox reactions transfer electrons between reactants. So we've had a little bit of experience with electron transfer back when we studied ionic bonds, and you saw one earlier in this lesson. It's when a strong guy, remember the metaphor, the strong guy takes an electron away from the weak guy. So for example, sodium chloride, table salt. Chlorine has a high electronegativity, sodium has a low ionization energy, so the high electronegativity means it pulls in electrons, so the chloride pulls in electrons well. The sodium, low ionization energy, does not hold on to its electrons well. It doesn't take very much energy to take an electron away from a sodium, so the chlorine is going to take an electron away from the sodium. That makes the chloride negatively charged, the sodium positively charged, positive, negative stick together. Now that's just simply for a chemical bond, an ionic bond. We're going to talk about how the electron transfer takes place amongst all the elements in a chemical reaction. And that's called an oxidation-reduction reaction. In fact, most reactions in chemistry are oxidation-reduction reactions. We've just never called them that up until this point. So in a redox reaction, again, saying redox and saying oxidation reduction is exactly the same thing. In a redox reaction, an element in the reactants is oxidized, which means that it loses one or more electrons. The electrons are passed to another element which is reduced, meaning that it gains electrons. Now, at first, when you first study this, that seems kind of backwards. Why is gaining electrons called being reduced? We'll learn that in just a few slides. So oxidized means losing electrons, reduced means gaining electrons. So the activity series shows that electrons will fall from zinc down to copper, so we've already seen that example. So the electrons are going to naturally move in this direction. Actually, we didn't see this example. This is the one that we're going to study, though, coming up. So copper is below zinc on the activity series. That means the electrons will flow from zinc to copper. They would not flow from copper back to zinc. Again, zinc is higher on the activity series. Copper is lower. An oxidation number in an ionic bond is the same as the charge number. So when you look at, we've been doing charge numbers for quite a while now. So if you look at your periodic table of the sheet called charge number by ion or 60 common ions, you'll see common charge numbers. So in an ionic bond, oxidation number and charge number are the same. It's basically showing whether that element is naturally going to want to gain electrons or lose electrons. Where it's different is with covalent bonds. In a covalent bond, the oxidation number is the charge on the atoms if the most electronegative atom completely took the electrons. So let's take an example of a water molecule. Water molecules are H2O, are covalent bonds. So they share electrons. That's the definition of a covalent bond. However, oxygen is more electronegative. We've talked about that many times. It pulls the electrons towards it, but it doesn't totally take the electrons away from hydrogen. So now, when assigning an oxidation number, we're going to assume that the more electronegative element, oxygen, does totally take the electrons away from hydrogen. So that would give oxygen a 2- charge, and it would give each of the hydrogen atoms a 1+ charge. Assuming that that oxygen totally took the electrons away. So again, let me say that. Oxygen doesn't totally take the electrons away from hydrogen, but when you're assigning an oxidation number, you act as though it does. The more electronegative one takes electrons away from the less electronegative element. That means oxygen would take the 2 electrons away from hydrogen, 1 from each hydrogen. That makes it a 2-, and each hydrogen would become a 1+. So in that case, hydrogen would have a 1+ oxidation number, and oxygen would have a 2-. So one other way that oxidation number differs is, particularly in covalent bonds, is that you can have a particular element can have more than one oxidation number. It just depends on what it's bonding with. Anyway, we'll see that in later examples. So the mnemonic for this is oxidation is loss of electrons, reduction is gain of electrons, and so the mnemonic is oil rig. Oxidation is loss for oil, reduction is gain for rig. That picture, if you don't know what an oil rig is what they use out in the ocean to drill oil, and so that's called an oil rig. So just remember oil rig. Oxidation is loss, reduction is gain, and that's referring to electrons. So oxidation is loss of electrons, so zinc is oxidized. Reduction is gain of electrons. So in the last example, copper is reduced. So there again, we see the same example. The zinc is going to lose the electrons. Copper is going to gain the electrons. And there we see the the same activity series, and you have a copy of the activity series in your reference sheets section. Let's look at what it shows you over on the right. We've never really analyzed it. So it's showing the oxidation. We never looked at that, said that before, because we had not been introduced to that term. But it shows the oxidation of each of those elements. So those are pure elements going down that on the left side of the arrow, and they're going to give away electrons, and it's going to show you the ion, the cation specifically, that they produce. So for example, lithium will give away 1 electron. We know that by looking at the periodic table. So it's going to produce the lithium ion plus 1 electron. So that's the oxidation of all of those elements over there. The reduction would be going in the opposite direction. You would just turn those reactions around. So for lithium, for example, it would be the lithium ion, the Li plus the electron would produce a lithium atom, an electrically neutral lithium atom. So this is a table of oxidations. So the activity series shows that electrons will fall in the last example from zinc down to copper. So oxidation is loss of electrons. Zinc is oxidized. Copper is reduced. That's reduction is gain of electrons. So there we see the same example. So zinc is called the reducing agent because it is causing copper to be reduced. This will make you a little crazy at first. The good news is we tend to not use these terms here, but it is the name of it. Copper is called the oxidizing agent because it is causing zinc to be oxidized. So an agent is something that causes something else to do something. In this case, the reducing agent causes the other element to be reduced. So zinc causes copper to be reduced. The oxidizing agent, copper, is causing zinc to be oxidized. So the summary, zinc is called the reducing agent and is being oxidized. Copper is called the oxidizing agent and is being reduced. I know it seems a little confusing, but it's just a little bit of practice. And as I said, we generally don't use the terms reducing agent or oxidizing agent a lot in class. Okay, so the transfer of electrons uses a bookkeeping system called oxidation numbers or oxidation states. Oxidation numbers have some common features to charge numbers that are used for ionic reactions. However, they are not exactly the same. So you're going to see a lot of rules here. Don't sweat these too much until we get to some actual examples. It's one of those things where you'll see a lot of rules, but once we practice some examples, we're not going to do that in this lesson. It will make more sense. So let's just read these though. Elements in their elemental form, that means they're not ionized, most stable form. It also not ionized, and also if they naturally form a diatomic molecule such as oxygen. They have an oxidation number of 0. So here, hydrogen has an oxidation number of +1, but H2 has an oxidation number of 0. So H2 is the natural form of hydrogen. You don't find hydrogen floating in the atmosphere just as an atom. It's as a diatomic molecule, H2 gas. For a monatomic ion, the oxidation number is the same as the charge number. So K is a +1. That's the same as your charge number for K for potassium. And oxidation is a -2. Nonmetals usually have negative oxidation numbers, but they can be positive. For example, sulfur can have oxidation numbers ranging all the way from -2 all the way up to +6. And again, when we get into some examples, you'll see how you can tell which that it should be. And hydrogen has a +1 when bonded to nonmetals and a -1 when bonded to metals. So again, examples will help clarify this later. Oxygen always has a -2 except in peroxide, such as hydrogen peroxide. That's what you use for elephant toothpaste. In that case, the oxygen would be a -1. Fluorine is always a -1. And other halogens, that would be chlorine, bromine, iodine, other halogens are -1 except when combined with oxygens. They are positive numbers. So again, it's a little crazy, the rules. Again, when we see some examples, we'll we'll deal with it then. And here are the rules for assigning oxidation numbers. Okay, so the oxidation numbers of the elements in a molecule must equal the charge. So if it's an electrically neutral molecule, then the 2 plus and 2 minus you would have to have 2 plus and 2 minus match up. If it was a charged ion, for example, a negative ion, then you would have a 1 plus and a 2 minus, for example. That would give you a -1 for the overall molecule. So they must equal the charge, whatever charge is on that molecule. Note, charge numbers are written with the plus and minus sign after the number, as in 2 plus. Oxidation numbers are written with the plus minus sign before the number, as in +2. And as you're going to see very shortly, I don't necessarily obey that convention. It's not necessarily significant. I'll try to obey it, but don't always do that. So don't worry about that too much. And some books don't even obey that. The most common type of redox reaction we will deal with is a single replacement reaction. We just saw that earlier, such as the following reaction between magnesium and hydrochloric acid. So this is putting a piece of metal into acid, a strong acid, and what happens then is the magnesium starts to dissolve and you produce hydrogen gas. So acid reactions, when they dissolve a metal, produce H2 gas. So the magnesium starts off as just a regular element, magnesium. And the hydrochloric acid, chlorine has a -1 charge, so you have 2 of them. Hydrogen has a +1 charge, so you have 2 of those. And so you have 2 HCl. Okay. And over on the right side, what has happened is the magnesium has given up 2 electrons to the acid, to the hydrogen specifically. So there's 2 HCl molecules there, you see. So magnesium gives up +2 charge. It gives up 2 electrons. And that's from your charge number of ion sheet. One of them goes to one of the HCl's, the other goes to the other HCl, and that turns the hydrogens into regular hydrogen atoms, a proton and an electron. And those 2, proton and electron hydrogen, get together to form a hydrogen gas molecule. Hydrogen does not exist just as hydrogen atoms. If there's another one around, it's going to pair up and join up with it and form a H2 molecule. So look at the magnesium. It started off as 0 charge. It gave up 2 electrons to those 2 hydrochloric acids, and now it has a 2 plus charge. So it's been oxidized. Its oxidation number has increased from 0 to 2. If you look at the hydrogen, hydrogen has an oxidation number of +1, but each one took on an electron from the magnesium. So now the hydrogen goes from each one being a 1 plus to being a 0. And that's when you form the H2 gas. And so the hydrogen is being reduced. Its oxidation number went from +1 down to 0. So now you see what the term reduce means, or reduction. It means that the oxidation number is being reduced. So hydrogen gained an electron, but remember, an electron is a negative charge. So that brings its oxidation number down from +1 to 0. There's exactly one element in any chemical reaction being oxidized and exactly one other element being reduced. You don't have multiple oxidations and reductions within the same reaction, at least not in this class. You won't. So in this reaction, magnesium is being oxidized from 0 to +2, and hydrogen is being reduced from +1 down to 0. So reduction refers to the value of the oxidation number. An oxidation number is given to each element in a compound, not to the entire compound. So it is individual elements that are being oxidized or reduced. Reduction gets its name because although electrons are being added to an element, the oxidation number therefore is being reduced. You're adding negative numbers to that element, so that reduces the oxidation number. Only 2 elements in a reaction are oxidized or reduced. In this reaction, chlorine's oxidation number does not change. You'll notice that. It stayed at -1 and you had 2 of them. So only 2 elements in the reaction are oxidized or reduced. In this reaction, chlorine's oxidation number does not change. It is a spectator ion and remains aqueous. This reaction can be broken into two half reactions as follows. Half reactions show the electrons gained or lost by each element. And this is an important part in understanding how batteries work. So if you take that reaction up above, there it is, rewritten. So you can write the oxidation half of the reaction. That's zinc that's being oxidized. So you take zinc in its pure form, that's the reactant in its natural form. It gives up 2 electrons and becomes a zinc 2+ cation. So that's the oxidation half reaction. So oxidation number of zinc is increased. The copper half of the reaction is called the reduction half because you have the copper 2+. It gains 2 electrons. That's going to reduce its oxidation number down to 0. So the oxidation number of copper is reduced. Just remember, so you don't forget which side the electrons go on, they go on the same side as the ion. So look at zinc. On the right side of that equation with zinc, the 2 minuses and the 2 pluses balance out to 0, and the zinc on the left side is 0, has a 0 charge. In the case of copper, copper has a 0 charge on the right side of the copper equation. That means the 2 copper ion pluses, 2 pluses, and the 2 electrons have to balance out. So the electrons always go on the same side as the ion. So electrochemical cells physically break these two half reactions into 2 different cells connected by a wire. So we're going to study this in detail in the next lesson, but I'm just introducing you to it here. This is called an electrochemical cell. So for the redox reaction to take place, the electrons will need to flow through the wire. So you see that if zinc is going to be oxidized, so that's oxidation on the left. The zinc is going to give up the electrons. For them to get over to the copper, they have to flow through that wire up above, and that voltmeter tells how much voltage, which is a measure of electricity. So this flow of electrons is called electricity, and this is how a battery works. So we won't say any more about this right now. We'll get into that in the next lesson. Alright, so that takes care of this lesson, just an introduction to electrochemistry and redox reactions and oxidation numbers, and we'll see how they work how they are all put together to show how a battery works and how electricity can be produced from chemical reactions.